Welcome everyone. We're here to talk about code scanning, scanning a lot of code, and potentially the lesson learned along the way, except I have to confess that it's a deception and it's a lie, because we've not learned much yet. We still have to do a lot of the work. When you scan potentially petabytes of code, things take time. So I'll show you where we go, what we hope we will learn, not every, and the things we've learned, but not everything that I was planning to show today, because we're not as far as we were expecting to be. So quick words, Philippe Ombredanne, I'm the maintainer of a series of projects called AboutCode. And what we're trying to do is provide open code, open data, and open standards to support what I like to say healthy and secure software supply chains. And we do that with projects like scan code for the code, data like what we're doing, what we're talking about now, for instance, in collaboration with Software Heritage, which we're doing on clear define, and a small standard called package URL or Perl, which is also used in many tools and vulnerability database and package database to unify them all. One thing that's special about us is that we're a non-profit for the public benefit, and everything we do is, as I said, free and open code, free and open data. So I cannot sell you something, but I think as we're putting together this non-profit foundation, your membership is going to soon to be due anytime now, if you want to join and help these efforts. Agenda for today. First, I'm not Google, I'm not Amazon, I'm not Meta. And dealing with petabytes of stuff is something that's really hard and new, especially when you don't also have all the resources to deal with that. And it's, at the scale we're talking about, everything is hard. I'll go through also some of the key parameters, what we're trying to do to optimize for speed, which is interesting because it's going to benefit everyone, whether or not you run one of the top 100 HPC computer at home, or whether you're just running a casual scan in your kitchen, you'll still be able to benefit of the speed improvements we're doing and some of the future things we want to consider there. So in my little neck of the wood, scanning petabytes of code is like really going to Mars or going to the moon. Probably, let's say moon, it's not as risky as talking about Mars travel, space travel these days. To give you a bit an idea of the scale of the problem, if you scan 30 billion files, storing 1 byte of scan result is 3 gigabytes. And that quickly adds up to a scale that getting results is a problem, where getting results is a problem. Storing results is a problem. Being able to extract results of the scan to make anything about it is a network issue. So every single thing is a small problem, and we further have to be careful because we're going to be given access to some of the largest HPC clusters in the world, one in Italy called Leonardo, another one in France called Janzé. And you have to carefully schedule and plan ahead to be able to use this stuff because they cost a truckload of cash to run. They use a lot of electricity and compute power and everything else. So everything needs to be carefully planned. It's not like you just run a batch on the side and you're done. I learned really, that was already a problem. I learned really like latency, network latency is a serious issue at that scale. It's really the biggest limiting factor is network access at this stage. Because they have terabytes of RAM, we have eventually petabytes of storage, so that's easy, but moving the stuff around is problematic. And another interesting problem is in the data we're looking at, software heritage, think of software heritage as a massive Git repository. Conceptually, but also actually in truth, it's a re-implementation of Git on top of a Postgres storage. The Git storage model on top of Postgres. And everything is duplicated. You're managing blobs. And the software heritage ID is essentially a Git SHA-1 blob. And when you have a blob, you'll have a file name. So a simple, stupid problem is, what's the name of a file when you have a SHA-1 blob? And you have 2,000 of these, or 10,000 of these, it's eventually the most common statically significant name for that blob of byte, which is things I would have never thought of being a problem. And why it matters, when you scan, say for license, a piece of code, say you have at the root of a package a file called license. Well, it has a certain signification and importance, which is more than any other file. So you need to know the name, you need to know the path. So that gives you a bit of the kind of problem with we're dealing. We're talking about multiple petabytes of code, anywhere between 20 and 30 billion files, and it's a bit in a state of flux because at the same time, software heritage is beefing up the archive and scanning more. So it's also a bit of a moving target in terms of size. Several hundred million projects. What software heritage tracks is every single piece of open source code that they can put their hands on. That's Git repositories, Mercurial, even Subversion, even CVS actually. There's still some out there. And all the archive from all the distros, all the package that don't exist otherwise in good repos. And we're trying also to do something like, filter large files. But say you have a JavaScript repo with a 12 megabyte yarn log file, which is a log file that lists the whole set of pin dependencies for that package. That's useful data. So you cannot blindly discard everything based on simple filters. So the original plan was to say, let's build a file system abstraction over the software heritage API, so we could reproduce on demand a file tree that would not be a statistical factory, but that would look from the point of scan code tools as if it were a real file system. And the problem was, we started eventually to have to do that for every single other tools they want to run on the archive, and that's not super funny to reproduce same code that's specifically doing file system abstraction for different tools. And really what's the direction's been taking to build a Fuse file system. A file system in user space, that's the name of Fuse, which expose something that resembles a file system in user space for any kind of tool. It's acceptably slow. It's not super fast, but having a common API and a simple no-code change way to access the archive is super useful. The other thing also, because of the problem of dealing with very large clusters, we're trying to warm up ourselves and stretch with smaller data set. And there's a good one from Hugging Face, which is called the Stack, which is just a couple terabytes, so sizable by all practical purpose when you do scans to stretch a bit your joints. It's also based on code originally from software heritage. It was also massively scanned several times with scan code, so it gives us also a bit of a baseline. They've used that to do responsible AI training for code LLMs. It's used also in their BCode project. It's also used, for instance, as a base for QuenCoder and a few other places that use code as an input. It gives us another. So when we go about doing optimization of the code, I like to think I'm super smart, and I can pinpoint where the problems are in the code without any help. Don't do that. You're not super smart, I'm not smart. Everything I thought about where we had performance issues were wrong. Literally, I went about, after discussing with a guy that maintains the RE2 library, which is a wonderful library for regular expression made by Google. I said, let's use it. It's going to be wonderful. And the problem is I didn't do any tuning, any benchmarking, any profiling. And the result is that it had absolutely zero impact. Like literally multiple days worth of work to switch to that, zero results. A bit of profiling and you find things that get you 20, 30% speed up just by using data. So whenever lesson learned, that's a real lesson learned, use data. Don't try to believe that you're smarter than the profilers and your hunch about your code, and I'm talking about my code here, your hunch about your code are wrong most of the time. The other thing is that most of our code is written in Python. And so it's a wonderful language, it's expressive, it's easy to read and debug, but we need native code for efficiency. And same thing here, after profiling, we found that one of the serious bottlenecks was some piece of code which does a diff between two files. Specifically, a diff between 50,000 license notice and files and York file. And when we go into that code, it was really going into something that was very slow. We found that through profiling, rewrote that, in this case in Cython, because that was the least minimal pass. I mean, a lot of people say, oh, you have to write in Rust and so on. Says, yeah, we have something which is a bit less involved, which is going to give us a good speed up. Again here, going native in Python can be super useful. But again, don't do that if you've not profiled first. We have another problem right now, which is how we're going to share this data. I like to liberate data as much as we can. I don't think data should be stored in a single centralized place that we can only access with a tiny straw. And that's a serious issue. The approach we're looking after is a design we call federated code, where we store not the code, but the metadata about the code, the results of the scans, say origin, license, information, dependency trees, copyrights, in JSON files stored in a constellation of Git repositories. Constellation, maybe, a couple thousands. The great thing about that is that then incremental synchronization is something that Git is really great at. And storing multiple versions of a scan with different versions of the same tool, or multiple scans of different versions of the same open source package. Compress super well, because you have typically a few increments and a few changes between different versions. And there's a layer of our activity pub, so that's something we already started to deploy, and we hope we'll be able to do that for that data, so it's available in software heritage, but not only. So, lesson to build on. As I said, I lied to you. We've not learned everything. We still have a lot to do there. The goal is to say, you should never have to scan twice the same open source package version with the same version of a tool, whether it's scan code today or other tools in the future. There's enough wasted energy and water with AI model training. Let's not compound that with scanning. And what I know today that a lot of our users are rescanning the same package over and over again. That's stupid, that's wasteful. So let's try to find a way to do that once and share that. We still have a problem to process this data, because the scan themselves is going to be in the range of 10 to 50 terabytes as a
Fermi estimate. Processing errors at that scale is a problem. And we've discussed the problem of storing. We want to make sure it's available. Why not share it with devs.dev as an example? I mean, all this, the point is to make sure that it's mirrored, replicated, easy accessible, easy to replicate in as many places as possible. In software heritage, but also not also there. Quickly, some expected outcomes. It's already having an impact on any scans you run. So if some of your company use scan code and run scan code in the cloud, that's going to be smaller bills, hopefully. We hope also to, we've already built some code. It's not AI, it's machine learning to spot inconsistencies in scan results to help say, hey, this needs attention. And we also hope that we'll be able to liberate these scans, so we build a database of fingerprints for doing code matching. We have a related project called the AI-generated code search, which is also a lie. It's not detecting AI-generated code. It's detecting if code that may have been AI-generated is strikingly similar to open source code that has been indexed. And for that, you need to be able to... So the point is in roughly 20% of the case, using a very unscientific approach, we see strikingly similar code copied by Gen AI from existing open source project, which is huge. And it's a problem. It's a problem on so many levels, but at least the point is that we need to have the tools, the data to support that so we can do that efficiently in the open. Thank you to Software Heritage for supporting this work as well as NLNet. Awesome. We couldn't be able to do that without it. We're, as I said, non-profit for the public benefit. I strongly encourage you, if you have a corporate sponsorship to spare, support NLNet's work, support Software Heritage, support us if you can too also, but start with these guys and join the community. So, questions? Any question? You're stunned, or you're bored, or you just...
I think we're at time anyway, so thank you, Philippe.
Post-luncheon breakdown. Well, that's
right.
it. You're welcome to join anytime if you want to have a chat outside, and thank you for spending your time there.
Thank you.